Okay, so this is the safety inspections for collegiate competitions. I'm Steve Lubliner, a longtime NAR member and a Triple E member. Okay, we're going to talk about several things today, what the problem is, what to expect during inspections at the two major competitions, the Student Launch Initiative and the Spaceport America Cup. And we'll get into specific problems that we've seen during inspections and what to look for. Yes. Okay. Back everybody. I have a little couple technical problems here. Again, I'm Steve Lubliner, NAR and Triple E member. What we're going to talk about today are what the problem is regarding inspections at collegiate competitions. Talk a little bit about the collegiate competitions and how we run the inspections, and then specific problems that we have seen at the inspections. Again, Steve Lubliner, NAR member, and professionally, I'm a retired engineer from aerospace companies. So the problem, the collegiate rocketry competitions are typically high power events. A lot of our participants don't have any experience with rocketry. If they did, it may have been a primary school or after school program like Scouts, but definitely very little experience with high power. We also have foreign countries at the Spaceport America Cup, and they don't have high power certification programs available. So the important message here is they don't have practical experience and they don't know what constitutes acceptable construction practices for the participants in these events. And we're going to try to identify our typical inspection processes, what we expect when people come to us during inspection, how we expect the rocket to be presented. And then finally, we're going to identify some of the conditions that we've seen that are pretty common and require correction. And oh, by the way, while this is presented as a collegiate competition, the information here is also applicable to your own rockets if you're doing high power or even more sophisticated model rockets. Also, if you're acting as a certifier or a mentor or flyer of record, the information in here is definitely applicable to all of those. So just the larger competitions, SLI, Student Launch Initiative, about 60 teams. Spaceport America Cup, about 110 to 130 teams, and roughly half of those teams are foreign. SLI is level 2 mostly. SAC is mostly level 3. We talked about international. SLI flies a bit lower. They fly 4,000 to 6,000 feet. Spaceport America Cup has two categories, 10,000 and 30,000. Spaceport America Cup allows non-functional, basically dead weight payloads. NASA will specify the payloads for SLI. This year it is a astronaut lander that is atmospheric independent. And finally, SLI does not allow non-certified motors. SAC allows non-certified motors. So the SLI is a 4-day event plus a rain day. There's one flight day. The launch is conducted under NAR insurance, and these are the two documents that are primary there, basically the NASA handbook and your statement of work from the team. They're limited to L motors, no hybrids, no clustered rockets, and all flights are subsonic. So the safety inspection, we basically have 2 days for inspection. So we need to process 60 teams in 2 days. Typical inspection will take about an hour, sometimes less if the rocket's really clean, sometimes more if the rocket has issues. And that's usually done off range at the Van Braun Convention Center for Student Launch Initiative. And then if we find issues, what they call the punch list, we'll do those inspections Wednesday through Friday. And then there'll be a final safety inspection, just like a normal launch at the launch site before going to the pads. Spaceport America is a 6-day event. We have 4 days for launches. We run Wednesday through Saturday out there. It's conducted under Tripoli rules and Tripoli insurance, except for the liquids. And they have what they call the design test evaluation guide. They have their rules for the competition, which is scoring and how to enter and the like, and also the Tripoli safety code. This event is limited to O motors. There are EX motors of hybrid, solid, and liquids, and student developed motors are permitted. I'm just going to finish. Okay, I'm going to finish this up. The safety inspections. The launch week is a Monday through Saturday, but we start inspections on the Monday of the launch week. We'd like to finish as many inspections as possible before we start flying on Wednesday. So Monday and Tuesday, we do the inspections at the Las Cruces Convention Center. So we're expecting about 120 teams this year. So over 2 days, that means we have to process 60 teams a day. So again, we'd like to streamline the process as much as possible that we can get everybody inspected before we go out for launch. And again, there'll be a final inspection at the launch site before you're cleared to the launch pads. So I'm going to just break away from this briefly, just make sure people are seeing the display. And I'm also going to check the chat. Okay. So Vince indicated, by the way, that the TARC teams have more, that go to SLI have more experience. And he is correct because they have participated in a rocketry competition. I don't have any questions yet. I'm just going to go back to the chat there, and then I'm going to go back to the slides. So what are we expecting? When you come to an inspection, what do you need to bring? Well, obviously you need to bring the rocket. We're going to have you basically disassemble the rocket for inspection. So any tools or fixtures you need to support the rocket, bring them with you. And you may want the fixtures because a lot of these rockets are anywhere from about 30 to 60 pounds, sometimes larger. So you may want fixtures to put them on while you're working on the rocket. We want you to bring your checklist because we will look at the checklist, and it is common to ask questions if things are in the checklist. We may ask for your supporting documentation. You should bring it with you, looking at your simulation printouts, especially like your rocket layout from Open Rocket or RockSim, because we'll look at, see if it matches what you said you were going to build. If there are any videos for any unique rocket functions or testing, we would like to see those. You should have what's called a fly sheet that has the basic rocket characteristics. We will probably ask things like static stability margin and velocity at the end of the launch rail and what the launch weight is. And the technical experts may ask for additional information regarding the experimental motors, hybrids, liquids, and solids. We'd like you to limit the teams to about 6 to 8 people for the inspection because we don't have a huge amount of area for the inspections. So there's space limitations. We've got a bunch of large rockets. And again, we're going to try to process 60 rockets a day. The team members that you do bring, they should be able to answer any questions that the inspectors have regarding anything about the rocket, basically. The team member, team mentor, and the flyer of record should be there, but we'd ask that they stay in the background. Again, this is an engineering competition. We want to hear the students talk about their rocket. So you're basically the fly on the wall if you're the mentor or flyer of record. Okay, how should the rocket be configured when you present it to us? We want the rocket ready for flight with the following exceptions. Okay, if it's a really big rocket, like over 8 feet in length, you might want to separate it for easier handling. Okay, we don't want any energetic materials during the initial safety inspections. No loaded motors, no black powder case charges. We do want the rocket motor casings installed. Because we've had problems where it turns out that the casing doesn't fit in the rocket, that some teams have just never bothered to fit it in. We don't want any tanks or assemblies pressurized unless they're not intended to be vented, like gas struts or single-use pressure cylinders. Expended ones would be nice if they're installed to show how they're mounted, because we're always looking for solid mountings on all the parts inside the rocket. If you have any mechanical stored energy devices like springs, keep them deactivated if you can. And we'd like no high voltages in the rocket, nothing greater than 50 volts in any of the stored electrical energy devices. You might think, well, who has stuff more than 50 volts? We have seen at SAC, some teams have run several hundred volts on some of their payloads and on some of their recovery electronics. Okay. Batteries, they should be installed for flight, but they can be electrically disconnected. We'll go either way on that one. They can be connected or disconnected. But we do want to see the batteries installed, because that's one of the biggest problems, is how well mounted are the batteries. All the recovery components, except the energetics, should be installed and rigged for flight. So one of the common issues is we'll see tape or bundling of the recovery harnesses and the like, that the teams tell us that they just did that for storage and to ease handling. If they do that, we're going to ask you to show in the checklists where is that tape removed, because in some cases that will prevent opening of the parachute. And what we typically do with the parachute systems is once we separate the section, we'll have you walk away with the two sections of the rocket, and we're going to see how easily the parachute recovery system comes out of the rocket. Does it hang up? Does it fall out? Is it super tight? So those are things we're looking for. Obviously, if you've got shear pins, we want those installed. If you've got any sharp nose cones or other components like fin tips, put protective covers over them, old tennis balls or foam or something. We're in close quarters during the inspection. So to avoid poking anybody in the head, whatever, we just put covers over your sharp stuff. And finally, and this is more often than not done, we want to see your team numbers, your center of gravity, and your center of pressure clearly marked, and not just a piece of tape someone stuck on the rocket. At least a Sharpie. If it's a decal or something, better still, but try to make it somewhat obvious. So when you come to the inspection, what are we going to do to your rocket? Okay, we're going to have a team typically of 2 or 3 individuals performing the inspection. Usually it's next available team does your inspection, unless the team includes your mentor or flyer of record. We don't want any conflicts of interest. You'll be filling out paper inspection sheets. We'll record any discrepancies that we find during the inspection. So inspectors, all of us have better ways of doing things. We may offer advice regarding best practices or improvements. If the advice is not written on the inspection sheet, it's not required to be accomplished. Only what's on the inspection sheet you're going to be held to. We may suggest for the future that there are better ways to do things, but again, that is not a requirement for fixing your rocket. Okay. By the way, a lot of this inspection process, if you're doing certifications like level, especially level 3, but even lower level certifications, a lot of this stuff applies as far as what to look for and how to do the inspection. Okay, we may ask you before we inspect your rocket, tell us about your rocket. Basically, how does it work? Because we don't we probably have not seen your rocket in the past, so we'd like to know just a general idea. How do you think things are supposed to happen? We're going to disassemble the rocket, typically order of flight events. We'll inspect, manipulate rocket components. We'll try to bend things, pull things, see if they come apart. Again, if there's something that's particularly delicate or something we should be aware of, identify it to the inspectors. If there's something we really need to know before we get into the rocket. We may also ask you to identify steps in your checklist. If there's a operation or something that we question or how it's set up, we may want to know that you've actually considered that in your checklists or that the teams have in their checklists. When the inspection is over, we're going to sign your inspection sheet. If there were no issues, even if there are issues, we're going to identify, we'll sign it, but we'll put the discrepancies on what's called the punch list, which is the Student Launch Initiative name, or what we call remediation, which is the Spaceport America Cup name for items that require inspection. And if there's no discrepancies, we'll sign off and say you're good to go. We also suggest that you take a picture of your inspection sheet. The multi-part forms don't carry through well onto the following pages. Payloads. So when we do the safety inspections, all we're really looking for is safe operation. We're not looking that you're compliant with the payload requirements. For example, for Spaceport America Cup, your payload is required to weigh a minimum of 8.8 pounds. We are not going to weigh your payload. There are other inspections, by the way, for Spaceport America Cup. They will weigh the payload. But as far as the safety inspectors, we will not. We will ask the student team to describe the operation of their payload. We want to know if there's any energetics in there, any high voltages. We've had some where we've had some biomedical concerns. So we want to know what's in the payload. If it is going to be deployed, and for this year for NASA, the payload is deployed potentially. What altitude? Is it automated or is it based on an operator command? Again, for SLI this year, it's based on operator command. You have to have permission to release your payload. How is it deployed? Is it spring loaded? Does it fall out? Are you using any energetics? And at what altitude does the payload deploy? In the case of SLI, I think it's 400 feet this year. We may also request that you identify steps within the checklist that document your safety and arming, your preparation or operation of payloads. So you've gone through the initial inspection. Congratulations if you've gone through the inspection with no issues. If you have issues, then you've got what we call the punch list or remediation inspections. And you have to go through follow-up inspections. So we need to clear those discrepancies before we can issue a flight card. Okay, we typically don't need the whole rocket for a follow-up inspection. All we really want to see are the parts, components, or documents that we flagged. So if it was an eBay issue, we don't need the booster. We don't need necessarily your payload. We want to see just the eBay items that we flagged. We don't need your entire team. It can just be one or two members of the team to show us and explain what the corrections were. And we can address all the discrepancies at the same time or separately. Some are easier to fix than others. So the punch list, and it's kind of catch where catch can. When we're doing the initial inspections, if we have a free moment and you want to come back to us, that's fine. Both major events have, I'll call them trade fairs. If you want to flag one of us during the trade fair, that works. If you see us in the hall, can we come to you with our rocket right now? That's fine. We're pretty flexible as far as doing the punch list and remediation inspections. Okay. We need to clear the item. Again, we don't want the rocket energized. We want the rocket in a safe state. And once we've addressed all the discrepancies, we will sign off on the inspection sheet and you can proceed with getting your flight card. So pre-flight inspections, this is more of a typical NAR or EEE on-field inspection. This is at the range. So for the rocket, okay, everything is installed. All the energetics, everything is basically ready to put on the pad. They all should be in the safe state, either turned off or restrained. If the electronics do not have energetic or energy release functions, they may be powered. So as an example, we'll talk about GPS. The featherweight GPS doesn't have any energetic or GPS functions, so there's no issues with leaving that on. But if you have like an altimetrum, like a telemetrum that's got GPS and it's also controlling energetics on your rocket, that cannot be switched on. We'll give you a last visual inspection. We're going to look for evidence of new damage, looking for missing components, and then we'll clear you to the launch pads. In the case of Spaceport America Cup, the rocket may be impounded if we're going to delay entrance to the range. So we'll hold the rocket until you're cleared to enter the queue for the range. So we'll go into inspection problems. I'm just going to shift back briefly and look if there's any questions or comments. Okay. So there is no specific SAC inspection sheet at this time, Chris. That's something I'll keep in mind because that's one of my areas of responsibility for Spaceport America Cup. So this presentation, we are talking about for Spaceport America Cup, there is a learning management system, and we are going to ask that the teams read this before the SAC. But as far as specific things we're looking for, we don't have an inspection sheet that does that right now. If you've got suggestions, what you want to see, you can either message me or put it out here in the chat because other people may have input. Yes, the slide, I will be more than happy to email you my slide. I'll give you my email address at the end of the presentation. You can reach me also through the NAR safety page. I am the NAR Safety Committee Chair, so you can reach me that way. We'll talk and see if there's some other way of making it available. Maybe the NAR forum would be a means, but I can definitely email it to you. That's not a problem. Okay, I am going to go back to the presentation. So again, the typical inspection problems that we see, this is not just limited to collegiate competition. This is probably good information for anyone that's doing inspections on rockets or when you're building your rocket. So as opposed to going through the list here, I'm just going to go into the topics. So electronics, okay, some of the electronics are critical. how they're mounted on the rocket. This You can see that it has an aft end identified on it. The reason is that it has a G switch on the lower corner. So let's see, you can't see my cursor on this, but in the lower left-hand corner of the board, you'll see that there's a G switch there. So if the board is mounted upside down, you will not trigger the timer and you'll have a flight failure. Some of the Altus Metrum is critical on mounting position. The old G-Wiz, which were accelerometer-based systems, were critical for mounting. Also, the mounting needs to be solid for these. If you've got a mounting that's kind of flexible, you may not transfer the proper G's into the box. So you may not trigger properly. Switch mounting and access. So the first one, which is kind of a head palm to the head slap, is can you get to the switches when they're mounted on the launch rail, when the rocket's on the launch rail? And believe it or not, we see that out there. So make sure that your switch panel or your access is not between your mounting buttons, that you can't get to it when it's on the rail. Toggle and slide switches especially, they're vulnerable to unintended operation from rocket accelerations. You can mount the switches perpendicular to the major acceleration forces, or as I'm showing in the pictures, you can use a locking device. In the upper left photo, the system is safed right now, and the locking device is in the safe position. And then for arming, the switches are up, and the locking device is in the locking them in the up position. The external push buttons and rocker switches, they're less vulnerable perhaps to G forces, but they're very easy to accidentally operate by rolling the rocket on top of them or just handling the rocket. So you probably either want to avoid push button and rocker switches or put some kind of a shield around them so they cannot be unintentionally operated. Rotary switches are maybe one of the better solutions. They're typically immune to acceleration forces. Two common solutions are the, I'll call it the voltage selection switch that you'll see on appliances. The other are key switches. One suggestion I would make is if you're using a key switch, put a spare key somewhere obvious on the rocket. So if someone other than you finds the rocket, maybe after the event is done, or someone other than you has to safe the rocket before you can get to it, they can do so. Or if you just forget your key, to bring it out there to the rocket. This is one of the most common problems. The batteries are not adequately restrained. Okay, tie wraps are commonly used, but they do allow motion, and especially if they can't be cinched tightly. I mean, it's typical to see a couple holes drilled in the sled and then tie wraps just strapping the battery down. That will work. I'd like to see maybe some two-sided tape or some Velcro or something in addition to the tie wraps to keep the battery more firmly attached. The battery should be restrained in all directions, as I show below. And you need to remember, batteries are heavy. Just a 1 ounce battery, if you've got 16 G's of acceleration, it's going to seem like it weighs a pound. Also, keep in mind that your battery restraints, for keeping your connectors attached. As you'll notice in this photo, even if the battery moves a little bit, the connectors can't come off. And that's something else that we look for during the inspections. Okay, we talked about restraints. Okay, you're trying to keep the batteries from moving during acceleration. You're also trying to keep the connectors on the battery during acceleration. So on the far left, you'll see that the batteries are forced onto their connectors during motor acceleration. Now, again, that nothing is a perfect solution because you've also got deceleration when the motor burns out. But usually your acceleration from the motor burn is going to be your highest G forces. So people will put batteries into the pre-molded battery holders. You need to be careful on those because, as I show here on the middle photograph, when you're at rest, the battery is making contact. You'll notice how much the spring is extended in that photo. Now we accelerate in the upward direction, like during boost. The battery will move backwards, and you'll see that the spring is compressed there, and you no longer have contact, and you no longer have electricity to power your electronics. So if you're going to use these types of battery holders, consider the G-force directions and go ahead and mount them in a direction where the G-forces are not as large. Too about batteries, by the way, Spaceport America Cup this year in their D-Tag, they're being much fussier about LiPo batteries. We had a couple LiPo battery fires last year. So the typical, I'll call them pillow pack batteries, if they come with or are recommended by the manufacturer of your electronics, they are permitted. Otherwise, they are not permitted. Basically looking for, a lot of teams are using either 9-volt batteries, like I show there. Another lithium battery that is permitted is the 18650 battery. And that battery is kind of like the small battery I show here as far as its connections. So you may want to use this type of battery holder and you'll have the same potential problems because those are cylindrical batteries. Eye bolts. So the strongest recommendation is the right-hand photograph, which are the forged eye bolts or U-bolts. And I think most people know what U-bolts look like, so I did not photograph a U-bolt. The bent wire eyes, which are typically provided by kit manufacturers, they're not permitted because they're going to straighten under high loads. They can be used if you weld the gap shut. We also look for locking devices on the attachment hardware because we don't want, if the swivel for your recovery system isn't working effectively, we don't want you unscrewing the eye bolt out of the rocket. We don't want any vibration causing things to come loose. So we suggest that you use things like nylon insert locking nuts, safety wire, thread lock adhesives like Loctite. I saw in some of the reports I was reviewing for Spaceport America Cup, there was a reference to carabiners. I'm not 100% sure if other countries have a different idea what the carabiner is, but the carabiners that are used for like your keys, like I'm showing in the photograph there, definitely not. They don't have the strength. Biggest suggestion is probably for the quick links, like I show in the middle photograph and the left-hand side. Distribution, okay. Like to see washers underneath the fasteners that you put through your bulkheads, trying to avoid point loads on the bulkheads. So fender washers are large diameter washers. You could see them on the photograph on the left, that they're under the nuts. You'll also see that there's locking devices on those nuts. So they spread the load, no point loads. And even on the inside, you'll notice same thing. We're using larger diameter washers to spread load. You also, in cases of, say, wood will try to compress, so it helps minimize some of the compression on the wood and fasteners loosening up. Okay, Terminal block connections. This is one that we commonly see. First off, we want to verify no loose connections. So we will do a mild tug on each of your wires to make sure nothing comes out. So you want to make sure that you have fully fastened your wires to your terminal boards. The other thing is we don't want to see any exposed conductors, no copper, basically. And the reason for that is that during G-forces, things may shift around. There's always a potential that they can touch. And I kind of exaggerated the case here for the left-hand photograph. Not a whole lot, but because we have seen stuff like this. But the best thing is no exposed conductors. Mounting of electronics. Okay. Bottom side shouldn't be touching the mounting surface. We don't want to stress the circuit boards. They're already going to be stressed enough during acceleration and deceleration. Use all of the mounting screws. You don't want to flex the board. Again, it just adds stress onto the board that can potentially break the board or break connections or loosen components on the board. Recommend the use of pan head or Philister heads because they're flat on their bottom. You don't want countersunk screws because you don't want to deform the printed circuit board. And I suggest the use of nylon hardware. There is a possibility that you'll have some vias or connections under there. You don't want to cut into those or accidentally cause shorts. So you'll notice that I use nylon screws where it attaches to the board, also nylon standoffs. Okay, wiring. Like to see good wiring practice, or we call wire dress. And you want to avoid any strain on connections. You don't want wires pulling free as they move around, pulling out of connections, or worst case breaking. You don't want. We want to avoid any pinching between the components and the edges that can cut insulation, again causing shorts. You have in your eBays or where wires transit, add a barrier, grommets. There was something we used to call Caterpillar, which was an edge grommet that glued over metal edges to protect wiring. So these are things you're trying. You'd like to see good wire dress. Also, one other note here, I talk about stressing the circuit boards. You'll notice I have a couple large capacitors on a perf board here, and those have epoxy on them. They're not relying on the leads to keep them in place. You want to pot them a little bit to keep them in place during acceleration. So a couple other items that we see, edges on components, especially at the ends of, like on ends of tubes. They can be a little bit rough. It may not seem like much, but you have a shock cord rubbing back and forth during recovery, and it will cut through a shock cord and wiring. So it's what we call breaking edges, lightly sand the edges to just break the roughness. Recovery system damage. We're going to look at your recovery system as we pull it out. We're going to see from previous flights if you have heat damage that's unacceptable, any tears in your parachutes. If you've got questions or you're not sure what the inspector is going to do with it, save yourself some time and energy. Replace them if you think that there's a potential an inspector is going to say no. So before I go on the checklist, I'm going to go back to the questions and answers. Okay, so Chris was talking about the R battery holders for cylindrical cells. Okay, so I would say is if you're using cylindrical cells, look them up. Try to stay away from the ones that use springs. Okay, I had no new questions. So for the chat, thank you for the advice, by the way, Chris. Going back to the slides. Come on, computer, you can do this. All right. Okay, so checklists. Checklists are one of the areas that are one of the biggest inspection issues that we have. Part of this is due to the inexperience of the college teams not having flown any really large, complex rockets. There's basically three types of checklists we're looking for. We're looking for final flight preparations, like installing the energetics, verifying the power source status, installing the flight expendables. We're looking for the pad checklist, is how are you going to arm your rocket? Final visual, do you have any covers or handling aids, lens caps on your cameras, for example? And do you have safing procedures in case we have to pull your rocket off the pad? Teams don't consider that they may not launch because we may pull rockets off the pad because of weather, for example. We also want to know that you have recovery checklists. For normal recovery, how are you verifying there's no live pyros? How are you capturing? Are you going to make sure you capture volatile data before you say switch off electronics? And how you're safing your systems. A normal recovery, it could be a shovel recovery. It could just be, the parachute sequence wasn't right. So you may be looking for your normal recovery items, plus capturing any failure data to figure out what went wrong. So good practice, you don't need for a good checklist to call out, tighten 36, tighten all 36 screws individually. You're not looking for excessive detail. You need to focus on the key tasks that are over and overlooked. So a checklist is not the same as a procedure. Procedure may tell you to tighten all 36 screws individually. A checklist is, are the screws tightened? And that may just be visual. That may be doing a sampling, just running your finger on them and see if you can do it by hand. But it's not a detail, check every screw. So don't spell out everything. And identify the mistakes that cause failure. If you know from the past that you failed a rocket because you didn't verify your voltage on your batteries, okay, that's something important to put on your checklist. The model suggested is use a read, do, confirm model. So read the item, perform the task, stop and confirm the task was performed correctly. What I allow when I'm working on pads is I allow two people at the pad for doing this. I allow the reader and the doer. The reader is also the confirmer. So the reader has the checklist, and I very, very strongly recommend paper checklists because computers are kind of unwieldy out there. They're hard to read in the direct sunlight. There's already enough noise and everything from rockets beeping and booping from their electronics. Use a paper checklist. And basically use the two-person, the read, do, confirm model. Do your checklist in a predictable order. Basically, you're going to power maybe the quietest electronics first so you can hear it. Then power your noisiest electronics so you're not trying to hear the quiet electronics. Those are things to consider. Think of it in terms of safety, because ultimately when you're done at the launch pad, the rocket's going to be somewhat hazardous. It's a rocket with energetics that's ready to go. So go from most safe to least safe. And then if you're backing out, from least safe to most safe. And of course, the advice here is we're not looking for just verification when you do a checklist. We want you to have a discipline out there for high performance. And that's the reason for the checklist. And I want to thank everybody. More questions. If you want a copy of this PowerPoint, this is my email address. You are all welcome to email me, and I will send out the PowerPoint. It may be, this one I think is about 10 meg in size. But at least for the right now, be happy to send out the PowerPoint. Going back to the questions and the like. Okay. Sam made a comment about using batteries with solder tabs. Only comment I have on that is don't try soldering directly to batteries that don't have tabs, because there's always a risk from heating the battery, they can explode. There are some places like Batteries Plus that have the ability to spot weld tabs on batteries. So if you want to solder directly to your batteries, consider having the tabs welded on them. And I agree, Chris, that is much better than holders. Going over to Q&A. Radio frequencies are an issue, Robert. At least in the case of Spaceport America, I know for sure that there's an operation called Da Vinci that is monitoring frequency control out there. So they want to know everything that you have that's radiating on board. And I believe NASA does the same thing, although I don't know as closely how they do their frequency control. It's a whole different set of subjects as far as electromagnetic compatibility with all the different radios currently on board rockets. I do have a PowerPoint stack on that. If you email me at the address that I gave previously, I'd be happy to send that to you. It has some basics for electromagnetic compatibility, things like twisted wiring, shielding, nothing that's super elaborate, but be happy to send that out. Okay, go back to chat. Okay, thank you, Chris. Thank you, Reggie. So anything else that people have? We've got another 4 minutes still. So I'm open to any other chats, comments. I'm also open to experience here too. If there's things that I missed that I maybe forgot about for inspection, like I did not talk about structural. There are so many varieties of how fins are mounted for Spaceport America Cup and even for SLI, that there's no common thread there that I could really present. I have seen some crazy stuff there. We had one team, I won't name names or countries, that had silicone rubber adhesive trying to hold their fins on. And that became even more of a mess when they tried applying epoxy over it. So there's things that the inspectors have that are not super common, and there's enough variety that I can't really put it into a PowerPoint. Thank you, Vince. And different mountings and stuff. Again, we look at the rail buttons because both competitions use rails. So one thing in advance we don't typically check is we don't check that the buttons don't interfere with anything else on the rocket typically. Although we do have a rail available to do that if there's a question. We do check to make sure that the rail buttons are well attached to the rocket, especially the aft rail button, because as the rocket comes off the rail, that's taking pretty much all the load. Okay, yeah, Jim, I've seen that too. No argument there. And I could probably add that on there. That just basic construction. I probably could add a slide on here as far as just look for things like uncured epoxies. The other thing we've seen too is when we pull it apart, just how did the joints slide? How well did the joints slide? My experience with fiberglass against fiberglass is it's very sensitive to any kind of dust, and it tightens up. So those are things we look for. Jim is also indicating, and it's, we do look at what's the capability components, which includes things like the quick links, the forged components, because of the snap loads when the parachute system deploys. So thank you for that, Jim. Yeah, Jim has participated quite often as one of the inspectors at SLI and SAC. He's also a mentor for some of the teams, so appreciate his efforts. And it looks like we're just about done. So again, just want to say, everybody, thank you for attending. Email me if you would like a copy of the presentation. And with that, I am going to stop the broadcast.